Hi everyone, back for another installation of Quadratics in Quarantine. Alright, so yesterday we talked about how we can have relationships that are both linear, they form a straight line when graphed, like what we did in grade 9, and that we can have relationships that when graphed don't form a line, they form more of a curve or a parabola, and we're getting into quadratics now. Alright, today's my ramblings are going to parallel the notes. I will go off on a few little tangents. I do like to try to compare quadratics to linear relationships just to give you a bit of a frame of reference. Quadratics, not that hard, but it can be super tricky until you understand it. So big focus here in this unit is trying to understand what's happening. Some of us had difficulty with linear relationships last year until we got it. Once it clicked, they became very simple to do. And quadratics is kind of the same thing. It's going to be a little bit tricky at first. Unfortunately, I'm not there to help you one-on-one hovering over your desk. But I'm hoping that it clicks for you sooner rather than later. So first of all, quadratics are relationships. If you remember last year, you were given with linear relationships, you were given the formula of y equals mx plus b. But you're also given, so that was y-intercept form, but you were also given standard form. So that was where ax plus by is equal to c. So that's standard form. Both of these are equations for a straight line. Same deal with quadratics. There's a bunch of different forms that we're going to be working with. So for standard form, that's this one. The standard form that we're going to be using today in quadratics is ax squared plus bx plus c. And so this is the quadratic formula in standard form. And so we're going to be exploring that today. Now, if I can refer you back to y equals mx plus b, the most basic linear equation is just y equals x. And if I was to graph that, that would give us a line that looks like this. Basically making a table of values for that. When x is 0, y would be 0. When x is 1, y would be 1. And so you have a point here at 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, so on and so forth. Then we started to add some things in, and I'll talk about more of this the next couple of days as well. I'll go over this example again. But these letters here altered this basic line. So if we change this from a 1 to a 2, because it's a 1 right here, we got a steeper line. And if we change it to a 3, we got a steeper line. And if we put a negative in front of it, well, that changed it to a line that looked like this. And then we had this b value. And what b value did is it raised and lowered our line up and down the y-axis. So right now, this is a plus 0. We leave it off. But if we were to make it a plus 5, that would shift our whole line up. So last year, our M and our B shifted the line. It made it steeper, less steep. It made it negative, and it raised it up and down on the y-axis. Well, with our quadratic equation, same sort of thing. This A, this B, and this C are going to change our parabola. Now, last year, linear relationships, we got a line. This year, we're going to get a parabola. And this parabola has a set of points. And then this nice, smooth curve that joins them all. And what these points are going to do is they're going to change where this parabola sits. So the most basic parabola, the most basic is y equals x squared. It's our most basic quadratic equation. And these letters here, sometimes it'll make this whole parabola shift up. Sometimes it makes them shift down. It might make it shift left or right. Sometimes it will make it widen. Sometimes it will make it narrower. So we're going to explore all those transformations. So you can see on your note, a parabola is this shape of a quadratic relation, and it can open upwards. It can also open downwards. Now for vertex, your notes are wrong here, and I can't go in and change them. They're in a smartboard file, and it's just a pain to try to change. But a vertex is the minimum or maximum point of the parabola. And so in this case, this point right here, the point where it looks like the two halves of the vertex meet, that is the vertex. In this case, our parabola is opening upwards. So this becomes our minimum point. If we have another vertex, I can draw it over here on our Cartesian plane. If it's opening downwards, our parabola, then this is the maximum point. And so your notes have this backwards. Your notes under vertex should say the maximum point is when the graph opens down, so change up to down, and the minimum point if the graph opens up. Now, with our vertex, so I'll draw a vertex here, and there's a lot of different points to it. And actually, let me draw in a Cartesian plane. So this is our x-axis and our y-axis. First of all, in this case, and it doesn't always have to be the y-axis, but this is our axis of symmetry. Both halves of this vertex are mirror images of each other. So it's the middle point in which both halves are the same. It divides it into two congruent parts, and congruent, of course, means equal. In this case, this is our y-intercept. This is where our parabola crosses the y-axis. In the drawing I drew here, it just happens to be on the vertex. It doesn't necessarily always have to be there. And these 2 points, these are our x-intercepts. And you can have 1, 2, or no x-intercepts. So if I was to draw 3 Cartesian planes here, here's an example of a parabola that has 1 x-intercept. Here's an example that has 2. And here's an example that never crosses the x-axis. So it's possible to have multiples there. So I know you do have this, but I'll go over it with you. So this is, I believe, on page 2 of your notes. And we can just label up some of these points. So I think the first parabola kind of looks like this. So this dotted line here, this is our axis of symmetry. This point here is our vertex. And in this case, because our parabola is opening upwards, it's also our minimum point. And our vertex is always written in x comma y as an ordered pair. We do have 2 x-intercepts here. There's 1 right here. There's 1 right here. This first one has a point of x1 and then 0. And this here would be our x2, 0. We do have a y-intercept as well. And it's located at 0, y. And likewise, I believe you have a second parabola here. So if we divide it into 2, we get our axis of symmetry. We have a y-intercept here, located at 0, y. We have 2 x-intercepts. This one is at x1, 0, and this x-intercept is at the second x value, 0. Our vertex up here is also our maximum point, or a maximum value. It's the highest value on that line. All right, last day we talked about first differences and second differences. So what we're referring to here are finite differences. And we know that first differences, if they're all the same, you get linear. And if second differences are all the same, you get a quadratic function. And I won't spend much time going over that. We did a bunch of that last day. All right. Let's do a question. I think we only have to do one question here, and then I could turn you over to your homework. So that's been given to you as example number 3. So we have a path of a baseball. So when that baseball is hit, we could imagine if we were to graph that hit, we would have time and we would have height. So when I hit a baseball, it would go up in the air, and then gravity takes over and it starts to fall down. So as at 0 seconds here is when you make contact with the ball. You can see I actually have a bit of a height here because the ball's not on the ground. It might be 3 feet off the ground when I hit it. And as time goes on, that ball gets higher and higher and higher in the air. And as time continues on, then it starts to drop back down. And it's actually going to hit the ground. And what we have here is a parabola. Now, mathematically, that parabola would extend like so. And so we do have a y value, you can see. We do have 2 x values in this case. With the idea of hitting a baseball, the solid line is the only part of the parabola that makes sense in this case. But mathematically, that whole parabola does exist. Now, so this parabola is defined by the equation of the height is equal to minus x squared plus 10x plus 2. So like last year where our m and our b changed the shape and the position of the line, same thing with these values. I will note that this minus x squared is really a minus 1x squared. So last year when we did linear equations, we would take our formula and we would come up with a table of values and we would graph it. So let's do the same thing. Let's do a table of values. So our x and our y. In this case, there's our x's and our y is going to be the height. So that's going to be the height. And let's come up with some random values. Now, because this ball, along the x-axis, we're going to be going from 0 seconds out to whatever seconds. I'm only going to do positive x values. I can do negatives in other situations, but knowing here that my x-axis is the time, I know that time when I hit the ball is at 0 seconds, and when the ball finally hits the ground is some seconds beyond time, so I don't have to get into negatives. All right, and I use my formula. Basically, I'm going to sub in 0 into this formula. So I'll write the first couple in here, and then I'll just do the answers for the rest. So for the first one, -1. So let's put in our 0 in for x, plus 10, 0, plus 2. So 0 squared is 0, negative 1 times 0 is 0, plus 10 times 0, which is 0 as well, plus 2. We get a value of 2. If I was to sub 2 in for x, and you can see that I'm subbing it in just for the x, and I'm putting brackets around to keep my work neater. So following BEDMAS, 2 squared is 4, negative 1 times 4 is 4, plus 20, plus 2. And actually, sorry, this is 4. Negative 1 times 4 is negative 4, plus 20 gives us 16, plus 2 more is 18. And when I sub 3 in each case, 3 squared is 9, times negative 1 is negative 9, plus 30, plus 2, we get a value of 26. This would be 26, 18, and 2. And you can see a pattern here. We got 2, 18, 26, 26, 18, 2. That makes sense. We know that our parabola is symmetrical. So there's our table of values. If we were to graph this, and I apologize, I tried to find some graph paper. I went out to a couple dollar stores, which are open. Couldn't find any graph paper. If I do contract the COVID virus, it was probably acquired at the dollar store. Those places are crazy. The aisles are about half a foot wide, and there's 1,000 people in there. So let's do our table of values here. And actually, I am going to scrap that one. And I'm just going to stick to the positive. So we got time and we got height. And so 0, 2, 4, 6, 8, 10, 12. So there's 14 seconds. And you can do these. Make sure you do equal spacing, equal intervals if you are. So I don't know, 4, 8, 12, 16, 20, 24, 28. All right, so plotting my points. We have here 0, 2. So 0 and 2 is a point. So we can see that when this ball was hit, it was hit 2 feet off the ground or 2 meters off the ground, whatever unit this is in. It says meters in the question, so I guess 2 meters off the ground. Our next point is at 2, 18, which would be right about here. 4, 26. 6, 26. 8, 18, 10, 2. And a nice smooth curve of best fit is going to give us something like that. There's the path of the ball. Axis of symmetry. The axis of symmetry is right here. So our axis of symmetry is at 5. That also allows us to know where our vertex is. So we know our vertex is at 5 something. And how high was the ball above the ground when it was hit? So how high did it actually get? And sometimes we cannot tell by just the graph. But we can go back and we can use our formula to figure this out. So our formula for this curve is height is equal to negative x squared plus 10 x plus 2. And what I'm going to do is, because we know that the vertex is at 5, that's our axis of symmetry, I'm going to sub in 5 for x, and I can find out the height. So height is equal to negative 5 squared plus 10 times 5 plus 2. 5 squared is 25, and that's negative 25 plus 50 plus 2. Negative 25 plus 50 is positive 25 plus 2 is 27. So we can see here that our ball reached 27 meters in the air. So that's how we use standard form to determine the height of the ball was hit. We could also, if we want to find out where did this ball land, we could sub that point back in as well. So that's when the height is at 0. So if we sub in a height of 0, we could solve for x, and that would give us our answer of exactly what time the ball landed at. So there you go, ladies and gentlemen. Hopefully that's enough to get you through today's homework. It should be. As always, if you have any questions, please don't hesitate to contact me, and I'll give you up a solution and send that to you. As well, as of filming this lesson, my YouTube page, I'm up to 7 subscribers now. Yep, that's right. I'm a pretty big deal in the YouTube world. Some of you have noticed, and probably why you've subscribed, is I tend to do these lessons up 3, 4, 5 days in advance of when they actually get published. I know some of you like to work ahead based on your boredom level or your work schedule. So feel free to subscribe too and begin to work a little bit ahead if you want to. That's it. Have a great day, everyone. Good luck.